Alrighty. Thank you everyone for joining, and thank you, Dr. Wagner, for your time. Today's webinar will be discussing the Ken Souza Memorial Student Spaceflight Competition, which honors the memory of ASGSR's longtime friend and leader by encouraging the next generation of student investigators to develop their own ideas for the future of gravitational research. Today's presentation is given by Dr. Erika Wagner, who is a Payload Sales Director at Blue Origin, and she works with research and education clients across multiple spaceflight platforms. Dr. Wagner will be giving a 45-minute presentation followed by a 15-minute Q&A session. If you have any questions that pop up during the presentation, please type them out in chat. And once we reach the Q&A session, then I will be reading those questions in the order that they were asked. With that, the floor is yours, Dr. Wagner.
Thanks so much. First of all, so nice to be here. I started my career as an ASGSR student member, and in fact, Ken Souza, for whom this program is named, was one of my mentors, was one of the ASGSR society leadership, and really took a number of us students under his wing and helped us to understand what was possible, and was really excited about giving opportunities to young researchers. So we are delighted to be carrying on this in his legacy, and I'll share a little bit about where we hope to go and what we hope to achieve. So my own background, I am a space life scientist by training. My doctoral work was my master's work looked at in human spaceflight adaptation, centrifuges, and vestibular physiology. My doctoral work was towards bone biomechanics and muscle adaptation to partial loading environments in rodent models. And for the last 10 years or so, I've been at Blue Origin, where I've been helping to enable roads forward for other researchers. So it's been this interesting transition out of academia and sort of into the industrial world. At Blue, we are dedicated to a future of millions of people living and working in space for the benefit of Earth. And we like to say that that's easy to say and hard to do, but it's sort of our guide star. It's what we think about every day as we come and develop a variety of different structures and systems that allow us to gain access to space. It's important to keep that why in mind. We have a philosophy here at Blue that we call gradatum ferociter, or step-by-step ferociously. And what you see on the left is our new Shepard launch vehicle, which I'll be talking about today. On the right is our new Glenn orbital launch vehicle, which is in development for launch out of Cape Canaveral. And it's interesting to think about these things as a continuum, right? What we are doing is developing systems and developing capabilities with the new Shepard vehicle. So it allows us to not only learn how to make the rocket engines, but to do the rocket operations. Sounds like we got someone with a hot mic there.
No, I got the link from Eventbrite.
Thanks. And so it allows us to develop capabilities, but also to develop markets and to start to really think about space as being accessible, not just to large governments, but increasingly to all of us. And I think that that's one of the things I love about the Ken Souza competition, is that it's saying all you need here is an idea, and you can come in and start to pursue your research in space. You don't have to go win the big NASA grant. You don't have to do tons of fundraising. This is on the merits of the science and the possibilities. So when I think about New Shepard, I love the videos that are out on our YouTube channel and the launches that we've been conducting. We just finished our 15th mission of this vehicle and are coming up on our first human flight. Really an interesting system. It has a separable crew capsule and booster. The system is designed to launch with a single BE-3 engine out of our launch site in Western Texas and travel up to the Kármán line, that boundary between space and Earth, right at around 100 kilometers. It has an escape system, which you see in some of these videos, but on a normal operation, it'll go up to a little over 60 kilometers before separating the capsule from the booster with a simple spring actuated system and giving us about 3 minutes of really high quality microgravity. The capsule comes down under parachutes with a thruster system that kicks up a lot of dust when it lands. And the booster comes back down and does one of these crazy Buck Rogers maneuvers to do a vertical landing. In some ways, it's a very simple system. In other ways, it's got a lot of complexity built in. the vehicle stands a little over 20 meters tall. It's really architected to carry 6 people or hundreds of pounds of payloads to these altitudes. So very capable and increasingly moving us towards an era where we can do a lot more things in space together. So let's talk about the basics of the Ken Souza Memorial Spaceflight Research Competition. This is run by the American Society for Gravitational and Space Research. It is open to all ASGSR student members. If you haven't joined, now is a great time to do that. It's not a terrible financial burden. If it is a financial burden for you, reach out to the ASGSR leadership and we will find ways to make that possible. Proposals for the competition. This is a space, life, and physical sciences domain. So we'll talk about the spectrum of things that are accessible here. The proposals are quite short. It shouldn't take you more than an afternoon to write. It may take you more time than that to really think about the details. So I encourage you to start soon. The deadline is June 3rd. But at the end of the day, the winner is going to take home a $1,000 grant and a free slot for a mini payload on one of our upcoming launches. We do have a few different categories that we are judging in, science and technical merit being sort of the lion's share of the evaluation, but also an opportunity to talk about how you're going to use outreach to share those results with your community. And of course, some evaluation of the feasibility and how does this science fit into the profile of a suborbital flight. So let's talk about how this, this is sort of contextualized in the flight itself. Here you see a schematic of that launch profile we were looking at earlier and the landing return trajectories, both the capsule and the booster going up over the Kármán line. The payloads for the Ken Souza competition are inside that capsule. And within that capsule, they are inside a locker, and within that locker, they are inside a small box that is of your design. So we'll talk about sort of those steps. Most of our experiments that are coming in, just by the nature of ASGSR, are focused on the microgravity portion of flight. But there's also an opportunity that you have a power on and ability to collect data through ascent and descent as well. And sometimes these G transitions can be really interesting. When we tend to look at things that are flying on the International Space Station, for instance, we might launch an experiment and it takes a couple of days to get installed and really start it up on ISS. So looking at those transitions from 1G to the higher Gs of launch to microgravity and back in, it allows for some interesting opportunities in both the life and physical sciences. As I mentioned, the vehicle's been flying for a few years now, 15 missions to date, including 10 with payloads. Those flights have let us carry more than 100 payloads from 7 different countries up to space and back. More than 40 of those for the NASA Flight Opportunities Program. So for those of you who are interested in technology development, that's a great place to be looking for sort of future funding opportunities. But I think that opportunity to think about this is an internationally open competition. It is one where we're excited to see the best ideas wherever they're coming from. Here you see the interior of the crew capsule outfitted for astronaut flights. So that will carry up to 6 astronauts. Every one of those is a window seat, so you get some incredible views at the largest windows ever flown in space in all of history. When we fly this in a payload configuration, though, we take the seats out and we replace them with stacks of payloads. So up to 36 lockers in a cabin. Each of those lockers is about the size of a mid-deck locker, if you're familiar with the space shuttle or space station standards, or a small dorm microwave, if that's a more convenient reference. Here you see the 4 standard interfaces that we fly on the vehicle. Again, the single locker is carrying 25 pounds of payload, about 200 watts of power provided. Double locker, twice that volume and mass. The full stack is sort of our largest standard interface. We can go bigger than that, but this is the largest one for which we have sort of standard boxes. And that gives you up to 150 pounds of payload and about 800 watts of power. But the Ken Souza competition works in our mini payload units. And so those are the product that we designed to be most accessible to students, regardless of sort of how you're coming in on your funding profiles. And those mini payloads are essentially the form factor of a 2U cube satellite. So 4 by 4 by 8 inches, 10 by 10 by 20 centimeters, half a kilogram of payload, including your structure. And we'll go ahead and provide you with power and data. So you don't have to do that interior to your payload. We're going to give you a USB connector that gives you 5 volts of standard USB power and a serial data stream from the vehicle. We can talk more about those. Here you see a box that was designed for flight. Lots of interesting approaches to designing that chassis. We've seen teams that 3D print them. We've seen teams that go out and buy them. We've even seen teams that go to the procurement, to the container store and just buy a box that's about this size. The loads of a flight are pretty modest. They're designed to carry you and I. So we're going to peak at a little over 2.8 G on ascent, short period of about 5 G on descent. So the structural power of your chassis is not usually the driver. It's more about how do you miniaturize the science and get it to fit inside. In terms of the constraints of the payload, we are talking about small quantities of liquids or batteries. If you need to have batteries because of a device that can't be run off of USB power, that is an option. But no significant hazards, no biology. That's going to be the hardest piece for the ASGSR community. We'll come back and we'll talk more about how that works. And shipping is L-2 weeks, so 2 weeks before the launch. That gives you an opportunity to really sort of finalize your design, make sure it's working on your benchtop before you ship it down to Texas. When we think about what fits into a basic payload box, there are ways to upgrade to advanced. We really encourage for this particular competition to stay within the basic box and sort of the product that ASGSR is providing. Want to think about keeping this simple. So you're talking about physics experiments, technology maturation. So if you're thinking about the way that we might think about art and design in this space, and how do we use what we know about fluid physics and what we know about microgravity development to allow us to explore that space. So here's a lot more words saying the same thing we said on the last slide. Flight environments obviously drive design. And so what you see on the left is an acceleration profile. The vehicle is vertically launched and vertically returned. So almost all of that is in the GZ, the vertical axis of the vehicle, the vertical axis of your payload. And again, you see about 2.8 G on launch loads, coming down for that nice long period of quiet microgravity time, and then peaking at about just a little bit south of 5 G as we come back in. If you are designing for off-nominal cases, and we sort of leave up to you how much of that off-nominal operations you want to be accounting for in your design, all we ask is that you fail safe, not that you necessarily fail operable, for those who are familiar with those terms. We do provide the shock environments for nominal loads, nominal missions, and off-nominal missions, so you can be aware of those. Okay, so what happens once you win? Once the award is made, we work with you and your school to get a contract in place. $0 contract. ASGSR is taking care of the expenses here, but we get you kicked off with our technical team. And there are 3 review milestones that you'll go through between selection and flight. The first is what we call our preliminary PDP, or payload design package. And that's a design review that's very similar to a PDR for those who've worked in the engineering world, where we're asking you to describe what are you doing? What is your concept of operations? What is your concept of design? What are your goals for your experiment? The next review is a couple months later. That's your final PDP, or your critical design review. There we're going to be asking you to show us all the details of your design, your structural design, your electrical schematics, your wiring diagrams. How are you thinking about testing your hardware to make sure that you're taking care of all the hazards that you're carrying with you? And how are you going to make sure that this is going to work every time autonomously? Once those final design packages are closed, test reports are due about a month and a half prior to the flight. That'll let us know that you've gotten all your testing done and you're ready to go. A month before flight, we'll start talking about the operations of the mission. And 2 weeks before flight, you'll ship us the hardware. So that's sort of the design cycle. We are happy to stretch that out. So nominally 6 months from contract signing to launch on a typical flight. We have definitely recognized that academic cycles may be a bit slower. So we've taken up to a year with some of these experiments. You let us know in your proposal what you think it's going to take you to get from award to ready to fly. So if you want to get more details on the mechanics of the competition, I encourage you to go to asgsr.org/Souza, and there you will find a lot more details about how the mechanics of applying for the competition work, where what we're going to be looking for is we're doing our evaluations, what is the role of a faculty advisor, and all those kinds of details. I'm happy to answer questions about that in our Q&A portion today. So let's turn and talk about science. 3 minutes is not a lot of time, but it's a lot more time than you get in a parabolic flight in a single parabola. And so we're talking about most of the science that flies on the vehicle is looking at relatively short time constant systems, ones that you can interrogate over the course of a couple of minutes. We'd like to find things where the data that you're collecting is really evident. So you either got visual signals that show when changes are happening, or simple sensors that you can gather that data. The most common science to fly on our vehicle across all of our payloads is fluid physics. That tends to work really well in this sort of time frame. Multi-phase flow being the lion's share of that, but also we think about technologies that allow for cryofluid management. In a 3-minute system, you're probably going to be looking at isothermal fluids, keeping temperatures the same, as opposed to wild swings in temperature and pressure. But we've been surprised at the creativity of investigators. Combustion is possible. In fact, our very first Souza award winner was doing a very simple combustion experiment. You've got to be thinking about how are you managing the byproducts of that combustion? Are there any hazards that you're creating? Materials science can be a nice, fruitful area. You're not going to grow large crystals, but small molecule crystallization, crystal initiation, melting, soldering, phase transition processes that happen in the timelines of flight can be really good targets. And then technology maturation. When we talk about the NASA Flight Opportunities Program, this is where the agency has done most of their investing. It's getting systems that work on your bench, but need microgravity time to prove that they're going to work in space, up to what's called a TRL, a technology readiness level of about 6 or 7. On the life sciences side, we have had investigators looking at a wide range of domains of acute responses to microgravity and those G transitions we were talking about earlier. Some physiological systems are clearly better suited to short flights, vestibular, pulmonary, gene expression, calcium channel signaling. For the course of the Souza competition, we do encourage you to think about what can you fly without actually flying model organisms. Model organisms come at additional cost and additional fundraising for a Souza team. So thinking about what are the technologies that you need to take your next set of steps, whether you're developing a cube satellite or an ISS payload, what are the technologies you need to show that you can deliver water to your plants, that you can exchange media for your cells, that you can image the kinds of samples that you need to image in flight. So start to think in that context of what can you do in 3 minutes in a simple design. Other markets that we serve, Earth and space sciences, folks looking out our windows, putting external payloads, not really as applicable here. We do have a capability of replacing that crew capsule with an 8,000-pound entry, descent, and landing system. Some really fun scale of experiments. And then, of course, student payloads starting small and as low as $8,000. We have a lot of schools that have gone out and done small crowdsourcing, talking to their departments, even things like crowdfunding campaigns to get to flight. I wanted to share a bit about the previous winners. So the first 5 years of the Souza competition were really fun to see the diversity of ideas coming across. The very first winning team was a combination between a high school and a university in Ohio, looking at oscillations in flame spread. They were using a flash paper solid combustion model and trying to understand what is the interaction between vibration and microgravity effects. The 2017 team looking at magnetohydrodynamic pump behavior, fluid physics, and technology maturation. In 2018, the University of North Dakota Dinonauts team used a very simple model organism of dinoflagellates, went out and raised additional funds to get those onto the vehicle, and looked at enzyme kinematics. So really starting to think about those biological processes and the transduction of signals in microgravity. 2019, the Soils in Space project led by Morgan Irons at Cornell University was looking at the mechanics and physics of soils and granular packing. And then last year, Alvaro, who we see hosting our meeting today, our winner looking at diamagnetic electrolysis and phase separation. So again, in the domain of fluid physics and technology maturation. So a really interesting spread from high school to graduate student, fluids to technology to biology. Really exciting every year to see what students are coming up with. A few lessons learned. It's helpful, I think, to think about this science as one giant, really clean parabola. This is not a little bit of space station time. If you think about science that's been done on parabolic flights, parabolic aircraft flights, and couldn't quite achieve its goals because either the G wasn't clean enough or the timeline wasn't long enough, you probably have a really great fit for suborbital flight. Picking a simple system with easily measured variables is really key. I think that we have seen the most successful experiments are the ones that can get really clean data from a camera or one or two sensors and be really crisp in the stories they're telling, and think really carefully about their controls, both in ground and in flight. The process of making the payload itself, there's options here. You can build or order a box, a chassis to put your payload in. It does count as part of your mass, that half kilogram, 1.1 pound mass limit. So you'll want to think about how you do that with mass efficiency. You see on the right here 2 units that are available from partners of ours. Purdue University provides their launch box. It's a very simple aluminum shroud and 3D printed end caps. Arete STEM provides the acrylic box at the bottom that gives you more visibility in ground testing and an ability to really drive that ground testing and see your system in development. The lab's going to have to be automated. We unfortunately can't fly student members at this time. I look forward to the day when that is the case. But this is going to be put your materials in the box and let the box be triggered by the rocket. So sensors or that serial feed that's coming from the new Shepard system can be your trigger. Most of these payloads have a simple microcontroller inside, like a Raspberry Pi or an Arduino. And then thinking a lot about your test campaign. I think it's something that we often overlook, particularly when we're talking about science, is the importance of rigorous testing. The engineering statement of test as you fly and fly as you test says that we should be thinking really carefully about that process. And we'd love to see that in proposals that student teams are thinking about how they're going to know that this is going to work. We often get asked about the challenges that student teams have faced as we've been flying so many of these payloads. So I grabbed a few of the highlights here. Autonomous operations in microgravity is not straightforward. So when you're thinking about that testing, does it work upside down? Does it work every time without having to poke at it? If you shake it first, does it still work? Is your construction techniques, are your setup techniques reliable and repeatable enough to allow for those kinds of loads you're going to experience in launch? L-2 weeks shipping it to us means that your system has to be able to sit on a shelf and sit on its side. We've had a couple of payloads where things dried out prior to flight. You really want to think about doing a full test run in your lab to make sure that those operational constraints are going to be consistent with your science. Build quality is hard. We often think about prototyping on the benchtop, but getting to flight quality hardware, thinking about all the basics. Are your wires neatly bundled? Have you made strain relief provisions and solid connections so they're not going to be shaken apart in the launch loads? It turns out that the harshest loads for most payloads are actually their shipping loads down to Texas. FedEx is harder than the rocket. So thinking about how do you prepare for those environments. Imagery is, as we said, is a common way of collecting data in these experiments. So you're going to want to be really rigorous in how you set up your cameras and your lighting to make sure you're not getting reflections off of other surfaces, that you've got the right focal length and focal depth at an adequate frame rate to capture the phenomenon you're trying to image. Thankfully, that's all really easy to test in your lab. And then last, preparedness. I know we have a tendency in projects to procrastinate. One of the things that rocket operations drives is to start to think about having a design freeze, which means that when you get to the end of those design reviews, you're not making more changes. So how did you get to the point where you're able to state with certainty what you're going to fly, and then show us that your as-built hardware matches what we reviewed? So good engineering practices. For those who choose to take on the role of additional fundraising, whether that's for your lab development activities or to pay your student team, or if you want to upgrade to additional capabilities within the payload, it's really been heartening to me to see that for such a low price, schools can have their own space programs now. We've seen local businesses provide sponsorship, government grants. NASA Space Grant is a great way to go if you're at a high school or university. Space grants are available in all 50 states. If you just Google Space Grant and your state's name, you'll find them. We've seen the foundations and school associations be good funders. At the K-12 level, PTAs are often a great source of additional funding. And we've also seen students just get creative, big sales, pancake breakfast, crowdfunding campaigns, even selling the ability to sign your name on the payload and send your name to space. I wanted to talk also just briefly about our Club for the Future program. This is our educational 501c3 nonprofit that we run out associated with Blue. Club is designed to get kids excited about futures in space and STEM and careers in the STEAM fields. So our first project here is called Space Mail. It gives students of all ages all over the world a chance to send a free postcard to space. If you haven't seen it, I encourage you to check out the Club for the Future website. And it's really just exciting to think about having something that you created go to space and come back and be hanging on your wall. We've flown tens of thousands of these postcards for students all over the world. And we do say kids of all ages. So feel free, if that's something that excites you, to participate yourself or to work with groups at your school to perhaps share that in your community. Here you see some of the postcards that we had coming in and just the fun that we have in processing those. Okay, I have a lot more I can say. I will try to save additional room for questions and answers, but just a reminder, proposals due June 3rd, asgsr.org/Souza for details, and really start thinking about what you can do in 3 minutes. With that, let me move to Q&A, and we've got some additional slides that we can come back to if that makes sense later on. Liz, where would you like us to start?
All right, thank you. First question, are rodents allowed to fly in the payload?
So for the Ken Souza competition, no, that would fall under biology, and shipping us a mouse 2 weeks ahead of flight, probably not a great idea. For our professional payloads, yeah, we are open to doing animal models. We have not yet had a rodent mission, but we've had a number of other model organisms that have flown in the capsule.
What information is provided by the serial feed, and will the winning team be provided with example data to work with?
Yeah, great question. So we have, if you'll send me an email at payloads@blueorigin.com, I can give you a lot more technical documentation. But in general, the serial feed provides two things. It provides state data for the rocket. So what's the altitude, what's the attitude, what velocity are you moving at, sort of the gross G levels and position, mission elapsed time. The other thing it provides is sort of in what mode is the vehicle operating. So it will tell you when launch has happened. It will tell you when you have entered the primary microgravity phase, so you can trigger off of that. It will let you know when parachutes have come out and a number of other different details. So it's all fed as a very simple serial stream of data that's easily processed by a microcontroller. Great,
thank you. Another question, does Blue provide subject matter experts that can provide guidance on design? The person that asked this question has no experience with electrical wiring, etc., and wants to know if they could get help with that.
Yeah, so that unfortunately is not part of our service. We would encourage you to reach out and maybe partner with other students at your school to think about how you would build a team that has those different pieces of expertise. We do provide our engineering subject matter experts as part of the review process, but they're really looking to verify that what you've done makes sense as opposed to do the design for you.
Okay, do we have any other questions? I think that was it for the chat. And for everybody on this meeting, if you do think of other questions later on, I did type out that email that Dr. Wagner mentioned earlier in the meeting chat to note down.
If we've got time, let me take a few minutes more to talk about some of the broader capabilities of New Shepard in the payload sense. I know we have a lot of university and graduate school level investigators on the line today, and it might be useful to sort of think about, where does this lead? Like, why might you do a smaller Souza payload in the context of a larger research plan? So let me just sort of talk about some of those additional capabilities and what's coming down the line as well. So in addition to what's happening inside the rocket, we've talked about the spectrum of things you can do in those single lockers, double lockers, full stack payloads. We're also starting to fly payloads on the outside of the rocket. And that's been really interesting. We did a series of technology development activities with NASA, culminating in a first mission on our NS-13 flight, where we were actually using the rocket as a model system for lunar landers. So in this case, we were doing terrain relative navigation, looking down at the ground, identifying hazards and using them to build maps for landing zones. And it was really interesting because it turns out when you go to the moon, you're tending to come down from a low lunar orbit, and that's in the sort of 70 to 100 kilometer altitude range. And the descent trajectory and landing maneuvers of New Shepard are actually a great model for that. So we were able to use New Shepard as a development platform for maturing both the sensors and the software that goes with them. We just announced, sort of in the theme of lunar work, which is so hot with NASA right now, we just about a month ago announced a mission where NASA is helping us to upgrade the vehicle for partial gravity capabilities. And this one's interesting because it actually takes the entire crew capsule and treats it as one giant centrifuge. So if you sort of think about a full vehicle rotation, the radius is about 1.25 meters at the center of those payloads. That gives us an 11 RPM rotation rate to have lunar G at the payload ring. And it lets us do a lot of interesting science here. So we tend to really understand well 0G and 1G. Hyper-G is pretty easy to test on the ground, but that domain between 0 and 1 is relatively underexplored. And so if we're talking about things like flammability and fire safety, there's some really provocative evidence that came out of the drop towers at NASA Glenn that showed that things were actually more flammable on the moon and Mars than they would be on the Earth or space station, because you're getting both diffusion limited and convection limited flame processes. When you look at things like flow boiling, some fluid behaviors are easily modeled with G as a variable. Others are much more nonlinear and chaotic, and understanding how do we think about those applications to life support systems, cryogenic fluid management, thermal management, propulsion becomes really interesting when you're talking about the lunar surface. Granular physics, things like regolith handling, plume-regolith interactions, electrostatic dust effects, something that is very hard to study on the ground, and we're excited to see what data we can interrogate in this system. And how that comes together for things like in-situ resource utilization, really both a multi-phase flow and granular physics problem. And of course, on the biology side, a lot of interest in what's going to happen to biology on the lunar surface. Is 1/6 G enough to trigger the key behavioral and sensing mechanisms in a variety of model organisms? Actually, a new procurement, it looks like, just dropped by NASA today, thinking about those lunar surface opportunities that are coming up in the Artemis missions. So this will be a first mission of this partial G capability. We'll be flying in late 2022. Not a great fit for the smaller payloads just because of the orientation of the G vector here. But if you're thinking about your lab writing additional grants to NASA, definitely something to keep an eye on. And then, of course, for me, the ultimate opportunity that's coming down the pipeline is to have human-tended payloads. We're coming up on our first human flight. We just had a really successful test flight and astronaut operations demonstration just a couple of weeks back. The human-tended payloads do some interesting things. We've had some of our experiments where they said, you know, I could go and automate this complex device, but it would probably cost me $1 million to build the automation and test it and make it robust enough for all the things that I'm interested in. And if I just had hands and eyes, that's a much more efficient operator. We've also seen the power of putting science in the hands of scientists. Any of you who've had a chance to work on ISS payloads know that the astronauts are awesome, but they do a lot on very little training. So if we can put someone into space that's not had 10 hours of training, but 10 years of training, that becomes a much more powerful opportunity to leverage expertise. A lot of interesting questions on what are the effects of spaceflight on the human body as we start to look at a much wider population of flyers, both in terms of having a large number of test subjects, a higher N design for your experiments, but also a wider set of population to work with. Astronauts certainly are chosen for their fitness and health, but when we look at the ways that investigations have used parabolic aircraft in previous years, it really gives you a chance to ask interesting questions for folks that may have implanted medical devices or different baseline physiology or different experiences with medications. So how do we use those unique test subjects to answer questions that we cannot answer today on ISS? So there's a program coming down the pipeline at NASA called Suborbital Crew. It lives within the Human Exploration and Operations Mission Directorate's Commercial Crew program. And the Subsea program is designed to give NASA a chance to fly both its own astronauts for training and mission operations development, but also NASA employees as researchers, which we're excited about. The Flight Opportunities Program through STMD, the Space Technology Mission Directorate, will do the same thing for investigators that are out in the university and corporate worlds. So keep your ears and eyes open. I'm really excited to see what happens when you and I get to fly with our own science. And then, of course, doing these bigger things certainly requires bigger resources. A lot of solicitations out there. The STMD Space Tech Ready solicitation, it's called Tech Flights, is coming out hopefully any day now, actually. It's usually right around this time. That provides up to about $500,000 for development of experiments and flight on suborbital vehicles. They are really looking in that solicitation for technologies that are working in your lab but need that flight time. So that's a great one if you've got tech maturation to think about. For more fundamental biology and physical sciences, the SMD ROSES portfolio, as we've seen the Space Life and Physical Sciences Research Group move over into the Science Mission Directorate. They've now come under that umbrella of SMD's ROSES solicitation. So what used to be Ross Bio and the fluid physics and fundamental physics solicitations will now be in that mode. So keep your eyes peeled for those. ROSES allows for suborbital testing as part of a science campaign. So a great way if you're really focused on the science data. And then if you have industrial collaborations, SBIR and STTR programs, a great way to work with small businesses to achieve these goals. The phase 2 and 2E and 2X SBIRs are a really nice fit to suborbital flights. Of course, if there's one thing that we've learned about doing commercial space flight, it's really that this is a new world. You don't have to go win a grant. If you can find other ways to fundraise those dollars, that's an open opportunity. You can just come buy a flight. So let me pause there again. It's a little bit broader view than we started with just the Souza competition. Any additional questions? All right. Well, looks like we've had a great conversation. Thank you so much for everyone who's been tuning in from all over the place. I hope to see applications from each of you for the Souza competition. We're really excited. It's not a heavy lift, but you do want to start early. So go visit asgsr.org/Souza. Go take a look at what it's going to take to complete that application and start building your team, find your advisor, and send us your thoughts. Liz, back over to you.
Thank you, Dr. Wagner. That was an excellent presentation. And yeah, really looking forward to seeing who wins the competition this year and what type of ideas come from this. Really appreciate your time and thank you for explaining the ins and outs of this competition. And if anyone has any questions once they start brainstorming ideas, again, that email payloads@blueorigin.com is in our meeting chat. You can write that down and send your questions to that email as they arise. And thanks everyone for attending, and thank you again, Dr. Wagner, for the presentation.